Good morning. Lecture 4 for Calculus 1. So last week we were talking about limits and continuity. Today we're going to start differentiability, very important, extremely important, the derivative of a function. It's chapter 3, and we're going to spend a huge amount of time on this chapter. But before I start talking about derivatives, are there any questions about limits or continuity?
Professor,
Yes.
I'm trying to go along with the textbook on Pearson, but it doesn't let me doesn't allow me to go on it.
What do you mean?
When I press when I go to Math 175 and then I go to the ebook and then I go to chapter 2.3 because that's
Yes.
what we're on right now, right? It doesn't let me. It says I have to download something, but it doesn't let me download it.
So for that, you need to go to the student help, the Math and Statistics Student Help Center in Gillette, where they can help you.
Okay.
All right, because yeah.
Okay. Thank you.
They also have on MyLab 2 versions of the book. There's a dynamic version and a static version. I know on my computer, I cannot download the dynamic version because they say I don't have the right operating system.
Yeah.
But I have no problem with the static version, which is basically the textbook page by page. So you might try that if you haven't tried it already.
Oh yeah, got it. So what page would we be on today?
So I'm going to do some of the review exercises at the end of chapter 2. That starts on page 128, 129, and goes to 130. And then I'm going to talk about derivatives in chapter 3, which is page 131.
Okay, thank you.
Okay. So I'm just going to start with some of the review exercises on limits. So I'm going to look at some of the problems in my version of the book on page 129. And we have typical problems are like this. This is number 21. So find the limit as x goes to 3 of x to the 4th minus 81 over x minus 3. And for this, you can't just plug in x equals 3 because you would get 3 to the 4th is 81. You would get 0 over 0, which is undefined. But we have to use factoring. And factoring is a part of pre-calculus that you need to know. We use it all the time. So there's certain factorization formulas that are really important, like x to the n, x squared minus y squared. Maybe I'll write it as x squared minus a squared is x minus a times x plus a. And x cubed minus a cubed is x minus a times x squared plus ax plus a squared. And x to the 4th minus a to the 4th, we can factor this in different ways. We can factor it as in the same pattern, x minus a times x cubed plus ax squared plus a squared x plus a cubed. And we could also think of this as x squared squared minus a squared squared, because x squared squared is x to the 4th and a squared squared is a to the 4th. And then using this rule, we would get x squared minus a squared, x squared plus a squared. And we could factor this again. This would be x minus a, x plus a, x squared plus a squared, and so on. There are different ways of factoring it. And in general, x to the n minus a to the n always factors. There's a factor of x minus a. And then you have decreasing powers of x down to 1 and increasing powers of a. This would be, they have to add up to n minus 1. This is a to the n minus 3, a to the n minus 2, plus a to the n minus 1. There's always a factorization like this. And again, the only way to understand this, if you're not familiar with it, though it should have been in your pre-calculus class, is just to write down lots of examples. So for example, if I have x to the 4th minus 81, then you have to recognize that 81 is 3 to the 4th power. So this factors into x minus 3 times x cubed plus 3x squared plus 9x plus 27. And then you can take this and put this in for the numerator here. So when you factor x to the 4th minus 81, you get x minus 3 times x cubed plus 3x squared plus 9x plus 27 over x minus 3. And then the appropriate miracle happens. The x minus 3's cancel. So we're just left with this polynomial. And for this polynomial, as x approaches 3, this goes to 27 plus 27 plus 27. You get 4 times 27, or 108. And that's the answer. Is there a question? I mean, don't hesitate if you have a question to unmute yourself and ask the question. Right? And let's take another example of this type of problem, something maybe a little bit simpler. Suppose I have the limit as, I can use different letters, p goes to 1, p cubed minus 1 over p minus 1. Again, you can't just plug in p equals 1, you would get 0 over 0. But p cubed minus 1 factors into p minus 1, p squared plus p plus 1 over p minus 1.
Podemos escucharte. Y siempre está.
I'm sorry, did someone have a question? And again, the p minus 1's cancel. So you're left with just this term, the limit as p goes to 1, p squared plus p plus 1. This is just a polynomial. As p goes to 1, this approaches 1 plus 1 plus 1, or 3. And let's look at some others, which are maybe a little bit trickier, but you have to get used to these sorts of things. This is problem number 24. We have the limit as theta goes to pi over 2 radians, sine squared theta minus 5 sine theta plus 4 over sine squared theta minus 1. Now, sine of pi over 2 is equal to 1. So as theta goes to pi over 2, sine squared theta goes to 1, minus 5 sine theta goes to minus 5 plus 4. you get 1 minus 5 plus 4, you would get 0 in the numerator. But in the denominator, you get 1 minus 1, which is also 0. That's 0 over 0. So to calculate the limit, you have to simplify this somehow. And if you want to, for example, this looks like a polynomial or a rational function in sine theta. Suppose we let, just to simplify things, x equals sine theta. Then what we would have in this problem is x squared minus 5x plus 4 over x squared minus 1. And these are just quadratics, and these you have to know how to factor. X squared minus 1 is x minus 1 times x plus 1. And x squared minus 5x plus 4, that also factors into x minus 1 times x minus 4. And the x minus 1s cancel. And we have x minus 4 over x plus 1. So this expression, so if you let x equal sine theta, when you write this in terms of x, you get this. So in terms of sine theta, this is the limit as theta goes to pi over 2. This numerator is x minus 4, sine theta minus 4 over x plus 1, sine theta plus 1. And now we're in good shape because as theta goes to pi over 2, sine theta approaches 1. So this numerator approaches 1 minus 4 or minus 3. And the denominator, sine theta goes to 1. 1 plus 1 is 2. So this limit is minus 3/2. Okay. What about number 27? So this is the limit as x goes to 5. Sorry, the limit as x goes to 5 of x minus 7 over x times x minus 5 squared. So what happens to this as x approaches 5? As x goes to 5, x minus 7 goes to 5 minus 7, or minus 2. So this numerator is approaching minus 2. What about the denominator? As x goes to 5, x times x minus 5 squared. First of all, this is a square, and this is positive. But x minus 5 goes to 0 as x goes to 5. So this is going to 0 through positive numbers. This is always, if x is close to 5, this is always positive. So this is approaching -2, and this is going to 0 through positive numbers. That means this is going to minus infinity. So this limit is -infinity because the bottom is always positive, approaching 0, and the numerator is negative. So you're going to minus infinity. Let's look at some more of these review problems, because these are things that you're going to have to see on the midterm and the final. This is number 36. So this is the limit of x to the fourth minus 1 over x to the fifth plus 2 as x goes to infinity. So in general, if you have a ratio of polynomials that is a rational function, and the degree of the denominator is strictly bigger than the degree of the numerator, then as x goes to infinity, this is going to go to 0. Let's see, and sorry, as x goes to infinity, this is going to go to plus or minus infinity. Let's rewrite this slightly. This is the limit as x goes to infinity. If I factor x to the fourth out of the numerator, I get 1 minus 1 over x to the fourth. And if I factor x to the fifth out of the denominator, I get 1 plus 2 over x to the fifth. And x to the fourth over x to the fifth is 1 over x times 1 minus 1 over x to the fourth and 1 plus 2 over x to the fifth. Now, as x goes to infinity, 1 over x to the fourth goes to 0. So 1 minus 1 over x to the fourth goes to 1 minus 0 or 1. And 1 plus 2 over x to the fifth, again, as x to the fifth goes to infinity, this term goes to 0, so this limit is 1. So this ratio, 1 minus 1 over x to the fourth over 1 plus 2 over x to the fifth, this goes to 1 as x goes to infinity. So this expression is going to 1, and as x goes to infinity, 1 over x goes to 0. So the limit is 1 times 0 or 0. That's what that limit is. Any questions about these? Let's look at number 66, where we want to find all of the asymptotes of a certain function. And all means the vertical asymptotes and the horizontal asymptotes. So in number 66, we're looking at the function f of x equals 2x squared plus 6 over 2x squared plus 3x minus 2. So we have a vertical asymptote where the denominator is 0. That is where 2x squared plus 3x minus 2 is 0. So where is this 0? Does it factor? That's an interesting question. So I think, let's see if this works. 2x squared plus 3x minus 2. Let's see if this factors into 2x minus 1 and x plus 2. So if you multiply this out, you get 2x squared. 4x minus x is 3x, and minus 1 times 2 is 2. So this factors. Or I could write this as 2 times x minus a half times x plus 2. And when I write it like this, you can see this is equal to 0 when x is either plus a half or x is minus 2. And if both of those places, this numerator is not 0, so let me continue this here. So I have this is number 66. So I have f of x is 2x squared plus 6 over 2x squared plus 3x minus 2. The numerator, if I want, I can factor is just 2 times x squared plus 3. And we saw the denominator factored into 2x minus 1 times x plus 2. Or I could write that as 2 times x squared plus 3 over 2 times x minus a half, x plus 2. And then these 2's cancel. And the denominator is 0 at a half and minus 2. So we have vertical asymptotes at x equal a half and x equal to minus 2. And it's also the case if you take the limit of this function f of x as x goes to either plus or minus infinity, that's the limit as x goes to infinity of, well, I can write it either way, x squared plus 3 over x minus a half, x plus 2, but these are both quadratic polynomials, x squared over x squared. This limit is 1. So this means we have a horizontal asymptote at the line y equal plus 1. So if we actually wanted to get some idea of what the graph of this function looked like, this is 0. This is the horizontal line, y equals 1. This is the vertical line, x equal minus 2. And this is the vertical line, x equal to 1. When x is, sorry, this is the vertical line, x equal to a half. When x is bigger than a half, these are both positive, and this is approaching 1. As you approach a half from the right, this is positive over positive, and it's going to 0. As you're approaching a half, the denominator is going to 0, and you have this vertical asymptote that looks like that. And when x is less than a half, then this is negative, and we're going to minus infinity. And this function is never 0, but we have another vertical asymptote here. And when x is less than negative 2, everything, this is negative times negative is positive. We have something which looks like this. So if you actually use Maple or whatever program you're using in your calculus lab to graph this function, you'll see vertical asymptotes at a half and negative 2, a horizontal asymptote at 1, and the graph of the function looks something like that. Actually, I'm curious for a second. So I'm going to open up Maple in my computer and see what happens. So I have the function f equal to, let's see. Share the screen with this paper. So you may not have Maple in your calc lab, or you may not be using it, have learned to do this yet, but in problem number 66, we have the function. Let's see. So my function is f, and x is sent to 2 times x squared plus 6 divided by 2 times x squared plus 3 times x minus 2. So that's my function. And if I want to plot f of x, did it correctly? I had caps. If I want to plot f of x, comma x. There it is. Let me do a little bit more, maybe from x equals minus 10 to 10. Exactly what I have sketched out. In fact, let me actually put in the horizontal asymptote, y equal 2. So, oops, sorry, horizontal asymptote was y equal 1. There we are. So here, these two vertical lines are the vertical asymptotes at -2 and +0.5. And here's the horizontal line, y equal 1. And you can see the graph of this function is approaching 1 as x goes to plus or minus infinity. And you see it goes to plus infinity as you approach a half from the right, and minus infinity is from the left, and so forth. So this is Maple graphing this function exactly, and you have this beautiful picture of the asymptotes. And if you wanted to know what is the limit of f of x as x goes to infinity, that's the question. And how do I get the answer? In Maple, I write limit with a lowercase l. Oops. Oops. Equals. There we are. The limit is 1. So if you go to plus infinity, the limit is 1. And if I change this to minus infinity, the limit is also 1. So that shows exactly that you have a horizontal asymptote at the horizontal line y equals 1 as x goes to plus infinity or to minus infinity. And in fact, if I take this out to 100, you'll see that it's so close, you can't even tell them apart. So here the function is never equal to 1, but It's so close to 1, you can't see it on your screen. That's the story. So let me stop the share and come back to our problem. So it's nice to see how Maple can actually solve your calculus problems for you. Okay. Any questions about this?
Are we allowed to use Maple for the midterm?
No,
Okay. Thank you.
but you can use it for your homework as much as you want, of course. And what program are you using in Math 155?
We're supposed to use Maple, but I still don't know how to download it or use it. So I'm going to the math tutoring center today.
Yeah, you definitely need to do that because do you have the like the password, the secret number you need to activate your program?
I think so.
All right, so they'll help you because they should know that. They're very good at that. And it's a big download. Sometimes it can, depending on your computer and the internet service where you are, it can take a long time or it could take a short time, but it's better to do it as soon as possible because it's a very valuable tool for learning calculus. Okay. So let's talk about something new. Well, actually, let me get. Are there any questions about limits or continuity that you'd like me to do right now? All right, then let's move to the main subject of this entire course, which is derivatives. So this is chapter 3. Derivatives. The other important part of calculus is integrals, and we do that at the end of the semester a little bit, and then most of Calc 2 is about the integral, and most of this course is about the derivative, but not all, of course, but so there's several ways to think about what the derivative is, but one very good way of understanding a derivative is to understand the rate of change of something. So, and there are two kinds of rates of change you might think of. You could have the average rate of change or an instantaneous rate of change. And we can think of this in terms of geometry or in terms of physics. It's all, the context might be different, but the mathematics is exactly the same. So let's think of, we have a function y equals f of x, and the graph of the function looks like that. And we want to know at some point on this curve, how fast is the function changing? So I can call the function f, or I can call it a, or I can call it s. It doesn't really matter at all. But so if this is the graph of the function y equals f of x, this point on the curve, this height, is f of a. This point has coordinates a comma f of a. And if we move to some other point x, this point on the curve has coordinates x, f of x. And if I want to have some sense of the average change in the function as you move from a to x, I can think of having this little right triangle where I've drawn the line between these 2 points on the curve. That's sort of the, sometimes called the secant line. And this distance from A to X is X minus A. And this distance from this height to this height is f of X minus f of A. And for this secant line, the secant has slope rise over run, f of X minus f of A over X minus A. So we can think of that as a kind of rate of change of the function as you move from A to X. The value of the function goes to from f of A to f of X. And something like the average rate of increase would be the height divided by the width, this over this. You go this much horizontally, and as you move from here to here horizontally, the function goes up this amount. So something like the average rate of change from A to X is f of A minus f of X over X minus A. How much you go up divided by how much you went across, which is the slope of the secant line. As you go from here to here, as you're going up this line, this is the secant line connecting these 2 points on the curve. The slope of the secant is this quantity. And that's something like an average rate of change. But if you want the instantaneous rate of change, not the average, you might take a smaller interval from A to a point X closer to A, and smaller and smaller and smaller. And these secant lines or the slopes of the secants, that would be the limit of this quantity, f of A minus f of X over X minus A as X approaches A. So you can think of it as you have this secant line, another secant line, another secant line, and in the limit, you approach a tangent line. So this limit, the instantaneous rate of change, is the slope of the tangent to the curve. That's how we interpret this at X equal A. And this number, so this is M for slope, M slope of the tangent. And this is what is called the derivative. So this is what we would call f prime of A. And we read this as f prime of A. This is one of many notations for the derivative. So the slope of the tangent line which is M subtangent. M we often use when you write y equals mx plus b for a straight line. M is the tangent. M is the slope, or f prime of A. We can write this as the limit as x approaches A of f of X minus f of A over X minus A. Or if we let X be A plus some small quantity H, as X approaches A, H approaches 0. This would be the limit as H approaches 0, f of X, that's f of A plus H minus f of A, and X minus A is equal to H. So these are two completely equivalent definitions of exactly the same quantity, which is the tangent slope, or the another interpretation. Suppose S of t is a position of a particle at time t. So the average velocity from t equal a to t equal to x is the distance traveled from time a to time x, that's s of x minus f of s of a, over the length of time it took to get there, which is from a to x, the difference is x minus a. And so the instantaneous velocity at x equal a, at a, would be the limit as x approaches a of s of x minus f of s of a over x minus a. Or again, if I write x as a plus h, that's the limit of s of a plus h minus s of a. A plus h minus a is h, as h goes to 0. And this is with the derivative s prime at a, or we write often v of a for velocity. The derivative of the position is, by definition in physics, mechanics, and everywhere, the velocity. So that is the definition of the derivative. And that's what we're going to be studying for a long, 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 long time. So let me compute some examples. Suppose we have a straight line. F of x equals 3x plus 2. So that's a straight line whose slope is 3 and whose y-intercept is 2. So suppose I want to compute f prime at a for some number a. That's the limit as h goes to 0 of f of a plus h minus f of a over h. That's the definition of the derivative. So this is f of x. What is f of a plus h? It's 3a plus h plus 2, or 3a plus 3h plus 2. So this is equal to the limit as h goes to 0 of f of a plus h, 3a plus 3h plus 2, minus f of a, which is 3a plus 2, over h. And this is nice because plus 3a cancels minus 3a, and plus 2 cancels minus 2. So this is just the limit as h goes to 0 of 3h over h. And the h's cancel, that's the limit as h goes to 0 of the constant 3. So what is this limit? Well, this doesn't even depend on h. So as h goes to 0, 3 is always 3. So for the straight line, f of x equals 3x plus 2, the derivative at any point a is equal to 3, which says the slope of the tangent line to this curve is 3. But this is a line. At any point, the tangent line is just the line. This line has slope 3, so the tangent has to have slope 3. And that's exactly what we discovered from this by using the definition of the derivative. But it's good. It tells us that what we expect should be the case is in fact the case. Any questions about this? Let me do a few more examples. Suppose I take f of x equal x squared. So the graph is a parabola. And suppose at some point on this parabola,
accidentally fired. He felt something in his face, but he didn't worry too much about it and just got on with the job. Life went on.
suppose at some point on this curve, I want to find the tangent line, or start with the slope of the tangent line. So that's find the tangent line to y equal x squared, let's say at x equal 1. When x is equal to 1, this is the point 1, 1. So what is that tangent line? So I want to compute f prime at 1, the derivative of the function at 1. That's the limit as h goes to 0 of f of 1 plus h minus f of 1 over h. That's the definition of the derivative at a equal to 1. So that's the limit as h goes to 0. What is f of 1 plus h? 1 plus h squared. What is f of 1? 1 squared over h. So now we have to do our high school algebra correctly. This is the limit as h goes to 0. The denominator is h. 1 plus h squared is 1 plus 2h plus h squared. And I subtract 1 from that. So the 1's cancel, and I have this over this. And from the numerator, I can factor out an h. This is h times 2 plus h. So this is the limit as h goes to 0 of 2 plus h, which is 2. So this tangent line has slope 2. And the tangent line goes through the point 1, 1. So now you have to do some more high school algebra, and you absolutely have to be able to do this. The tangent line has slope 2 and passes through the point 1, 1. So the equation of the tangent line by the point slope formula is y is equal to the slope 2 times x minus 1 plus 1. This is the point slope formula. This is the equation of the unique line with slope 2 that passes through the point plus 1 plus 1. So this is 2x minus 2 plus 1, 2x minus 1. So 2x minus 1, y equal 2x minus 1, is the slope of the tangent line. So just so I don't have all the fun, let me give you a problem to work on for a couple of minutes and find the slope of the tangent line and find the equation of the tangent line to the function f of x equal x cubed at x equal to minus 1. So just so you have some idea of this, I mean, you should be able to do this, I hope. But the graph of f of x equal x cubed, cubic curve looks like that. And when x is minus 1, y is minus 1. So that's the point on the curve. And at that point, there's a tangent line. So find the slope and the equation of that tangent line. So I'll pause for a minute and give you a chance to think about that. So you need to start by setting up f of 1 plus h minus f of 1 over h, which is what? F of x is x cubed. So that's 1 plus x cubed, 1 plus h cubed minus 1 cubed over h. So you need to expand this, simplify it, and see what you get. Let's see, if you expand 1 plus h cubed, you get 1 plus 3h plus 3h squared plus h cubed minus 1 over h. So in this, the plus 1 and the minus 1 cancel. So I'm left with these three terms, and there's an h in each of them. So I can factor out the h in this numerator. I get h times 3 plus 3h plus h squared over h. And now the h's cancel, and I'm left with just this polynomial 3 plus 3h plus h squared. So if I take f of 1 plus h minus f of 1 divided by h, and I do the algebra and simplify, I just get this quadratic polynomial in h. And what I want is the limit of this as h goes to 0. And as h goes to 0, these two terms disappear. I just get 3. So for my function, f of x equals x cubed, the derivative, oops, I'm sorry, I made a mistake. I put in h equal 1 instead of minus 1. So what I just calculated was at the point 1, 1, the slope of the tangent line. So since that's what I calculated, let me calculate that line first. So this tangent line has slope 3, and it goes through the point 1, 1. So the tangent line at 1, 1 is y equals the slope 3 times x minus 1 plus 1 is 3x minus 3 plus 1, 3x minus 2. So y equal 3x minus 2 is the slope of the tangent line at 1. But because I had asked for the slope of the tangent line at minus 1, let me do that. So we still have the algebra is the same. Well, maybe not. Let me just do it again. So I have my function, f of x equal x cubed. Looks like that. And f prime at minus 1 is the limit as h approaches 0 of f of minus 1 plus h minus f of minus 1 over h, which is the limit as h goes to 0, f of minus 1 plus h, or h minus 1, is h minus 1 cubed minus f of minus 1, which is minus 1 cubed, over h. This is the limit as h goes to 0. H minus 1 cubed is h cubed minus 3h squared plus 3h minus 1 minus 1 cubed is minus 1 minus 1 is plus 1 over h. So again, these two numbers cancel, and I have the limit as h goes to 0. If I factor in h out of this numerator, I get h times h squared minus 3h plus 3 over h. And the h's cancel. And as h goes to 0, this limit is 3. So this tangent line going through the point minus 1 also has slope 3. So the tangent line at minus 1 is y equals 3 times x minus 1 minus 1. So that's 3 times x plus 1 minus 1 is 3x plus 2. So the tangent line is y equals 3x plus 2. And that's their derivative. So this definition of the derivative is very important, and there usually is a question on the midterm or the final. The final is made up by the department, that asks you to calculate the derivative using just this definition. So let me do a few more examples. So remember the basic definition of the derivative. The derivative of f of x at x equal a, I can write it in two equivalent forms. So f prime of a is the limit as x approaches a of f of x minus f of a over x minus a. Or I can write as the limit as h goes to 0, f of a plus h minus f of a over h. And there are other notations. This is also sometimes written as df dx at a, or capital df at a. We'll see these other notations shortly, but there are many different notations in common use for the derivative. So let's compute. Suppose f of x is equal to square root of x. Compute f prime at a for any a. So let's see, let's use this definition. I like that one. So f prime of a is the limit as h goes to 0 of f of a plus h minus f of a over h, which is the limit as h goes to 0 of the square root of a plus h minus the square root of a over h. And this is a very complicated mess, and I need to figure out a way to, because right now as h goes to 0, the numerator and the denominator both go to 0, and that's not defined. So I need to see if I can make this more intelligent or more calculatable. And I can use the fact, which we use a lot in calculus, that, we could say, we know that u squared minus v squared is u minus v times u plus v. That's one of the basic differentiation formulas. If I have u minus v, I could think of this as, let's say u and v are positive, as the square root of u squared minus the square root of v squared, because square root of u squared is u, and so forth. And now I can use this formula. This is square root of u minus the square root of v, square root of u plus the square root of v. And you see, here I have a difference of square roots. Here I have a difference of square roots. So I have sort of this general strange formula that the square root of u minus the square root of v is u minus v over the square root of u plus the square root of v. So I have this purely algebraic identity for positive numbers. So if I let u equal a plus h and v equal a, the square root of a plus h minus the square root of a is a plus h minus a over square root of a plus h plus the square root of a. Right? I'm just using this formula with u equal to a plus h and v equal to h. And a plus h minus a, this is just h over square root of a plus h plus square root of a. So this numerator is equal to this. And if I divide by h, I get this. And here, the h's cancel. So here's a miracle. This is 1 over the square root of a plus h plus 1 over the square root of a. So this expression simplifies to this. So if I take the limit as h goes to 0 of this, that's the same as the limit as h goes to 0 of this. And as h goes to 0, a plus h approaches a. So this approaches the square root of a. So I have 1 over the square root of a plus the square root of a, and 1 plus 1 is 2. So I get 1 over 2 times the square root of a. And now, miraculously, I just calculated the derivative. That's really great. So let me go through this again, because this is a very important calculation. So we have a function f of x, and this is the definition of the derivative. F prime at a is the limit of, as x goes to a, of f of x minus f of a over x minus a, or equivalently, the limit as h goes to 0 of f of a plus h minus f of a over h. So that is the definition, and the hard thing, of course, is to turn this into a computation that you can do. So let's take a function, which is not the world's easiest function, it's the square root of x, which is only defined, of course, for x positive, or x greater than or equal to 0. And the graph of the square root function looks like that. Right? That's what f of x equals, or y equals the square root of x. And I want to find the derivative when x is positive. So any point over here. So that's f prime at a. Right? Here's a. Here's the tangent line to the square root function. I want to find the slope of this tangent line. That is f prime of a. So I'm taking f of a plus h minus f of a over h. That's the square root of a plus h minus the square root of a over h. And I use this bit of high school algebra, but it's a little clever bit. And I can rewrite this expression ultimately as this. So you need to like double check this calculation and see how I get from here to here. And then the limit as h goes to 0 is 1 over 2 times the square root of a. Right? So this is the kind of calculation which in calculus you must master. Let me do one more example, and then I think I'll quit for the day, because learning the derivative is hard. Suppose I take the function f of x equal to 1 over x, for x different from 0. So this is a hyperbola that looks like that. That's the graph of the function y equals 1 over x. So f prime of a is the limit as h goes to 0 of f of a plus h minus f of a over h. That's the limit as h goes to 0. My function is 1 over x. So f of a plus h is 1 over a plus h minus f of a minus 1 over a all over h. And I want to take the limit of this as h goes to 0. So I need to do some high school algebra to simplify this expression. So I have no alternative but to do the work. I have in the numerator 1 over a plus h minus 1 over a. So I'm subtracting fractions. So let me subtract the fractions. You have to put things over a common denominator. A common denominator is a times a plus h. So this is a over a times a plus h minus a plus h over a times a plus h. Here I multiply the numerator and denominator by a. Here I multiply the numerator and denominator by a plus h. So now everything's over a common denominator, a times a plus h. And I have a minus a plus h. A minus a plus h is a minus h. So the a's cancel. This is minus h over a times a plus h. So here, where I have this divided by h, 1 over a plus h minus 1 over a, all divided by h, is minus h over a times a plus h, all divided by h, which is minus h over h times a plus h. And these h's cancel. So this simplifies into minus 1 over a times a plus h. That's what this expression in the parentheses is. This is, so f prime of a is the limit as h goes to 0 of minus 1 over a times a plus h. And as h goes to 0, a plus h goes to a, and a times that goes to a squared. I get minus 1 over a squared. And that's my answer. So for the function f of x equal 1 over x, the derivative at any point a different from 0 is minus 1 over a squared. And you'll notice whether a is positive or negative, a is positive, a squared is positive. So minus 1 over a squared is negative. That says everywhere the tangent line has a negative slope. And if you look at this, wherever you were to draw a tangent line, it's always going down. All the slopes are negative. So this is consistent with our picture. So what I've just talked about is basically all of section 3.1, introducing the derivative. And this really is fundamentally important in this class. You really need to study this section at great length. And to also to review these calculations that I've done, as well as the calculations in the book, to understand how to use the definition of the derivative to calculate an integral, to calculate a derivative. Any questions about anything that we've done today? So let me remind you, this week, just as last week, I have 3 scheduled problem sessions. Tonight at 7, Wednesday at 1, and Friday at 11. And you're welcome to log on and ask any questions you might have about the theoretical material or how to solve any problems. And also, if you have questions and you can't make one of those times, email me and we can set up a time when we can meet on Zoom. Okay. If there's nothing else, then we are done for the day. So everyone study calculus, enjoy the weather, which is not as cold as it was over the weekend, and we'll be back on Wednesday. I remind you that next Monday, school was closed. I guess it's President's birthday. So we have class Wednesday, and then the subsequent class is a week from Wednesday. Okay, all. See you Wednesday. Bye.